So this is intended to be a quick revision video for all of motion for Edexcel 9 to 1 GCSE. It's the first part of topic 2. Topic 2 is motion and forces, but I've split it into two halves, motion and forces. I'm going to try and keep it snappy. There might not be as much explanation as normal, but hopefully it's useful if you've got an assessment on this or coming up towards the end of your GCSEs. So we're going to start with scalars and vectors. So a scalar is a quantity that has a magnitude, which means a size, but no direction. Whereas a vector, which you sometimes come across in maths, are quantities that have a magnitude and a direction. So really common examples of this are distance and displacement. If I said to you, I've walked 3 meters, that's just a size, that would be a distance, a scalar. And if I said I've walked 3 meters to the left, that's a vector, it has a magnitude, 3 meters, and a direction. So examples of scalars, common ones are distance, also speed, mass, energy, and a funny one they don't always talk about in the GCSE is time. Time can only go forward, so it doesn't have a direction because it can't go backwards as much as we wish that might be true. Vectors are anything that you can say, really, the number to the left. That's quite a good check. So if you, for example, you can say a force of something is 5 newtons to the left, that works. So vectors, examples include displacement. That's the vector version of distance. Then there is a vector version of speed, that's velocity. They're the main kind of vector pairs. Everything else is not quite a pair. So mass pairs with weight, but it's not the same thing, so we can't put it as a pair really. Weight is an example of a force. That's why it's a vector. Forces are very famously vectors. You use arrows to try and explain to draw them. Momentum is another common one. So there's many more, but these are the ones you're expected to know in the GCSE. So we're going to focus now on distance and displacement. Quite a standard kind of pairing. So distance is the scalar and displacement is the vector. Now imagine that I've walked this journey. I've travelled 4 kilometres to the north and then 3 kilometres east. The distance that I've travelled is the total length that I've walked. So I'd have travelled 4 plus 3, which is 7 kilometres in total. The displacement is the total distance you've travelled from the start in a straight line. So here the displacement would be this arrow there. Now if you know any trigonometry, you'll know that the hypotenuse of this is going to be 5 kilometres. I've done the square root of 3 squared plus 4 squared to get to that. So the displacement, the distance from the start would be 5 kilometres, and I need to put a direction. I could work out the angle here and measure it with a protractor, or I can just say north, east, which it basically is here. So at GCSE you can normally just state a direction, but later on you start to use angles to help with that. Another famous scalar and vector pair are speed and velocity. So we're going to have a look at those. Speed is the rate of change of distance and velocity is the rate of change of displacement. And you'll notice that distance, this is the scalar, so speed is a scalar and displacement's a vector, so velocity is a vector, which I've only just noticed the letters match up with the first letter of the word. Now the word rate in physics means divide by time. So speed equals distance divided by time, and velocity equals displacement divided by time. Now, in reality, we kind of treat these two things as very similar to each other. We just say that velocity is speed in a given direction. So if I said I'm travelling at 30 miles an hour, I've said a speed. If I say I'm travelling at 30 miles an hour south, it's a velocity. And we generally use the same equation because both of these equations, if I put them to symbol form, will look the same. And the symbols for speed or velocity is V. The symbol for distance or displacement that Edexcel use is X. You might see it written as T in other places. Sorry, not T, S. And then time is T. So this equation works for both of them. This, it should point out, is generally the average speed if you use the total distance. So if you have total distance over time, this would give the average speed. Now the units of these things, the unit of x should be the metre, the little square bracket means unit. The unit of time is second, which means the unit of velocity or speed is distance divided by time, or metres divided by second. It's the metre per second. Now, for Edexcel, you need to know some typical speeds. There's quite a few that you're meant to know, but these are ones that seem to come up quite a lot. Walking, the typical walking speed is about 1.5 metres per second. This is on average. You might walk faster, you might walk slower. Running, I always think about Usain Bolt. So Usain Bolt, when he's doing his record-breaking runs 100 metres in just under 10 seconds. 100 divided by 10 gives me 10. So running is always going to be less than 10 metres per second, because if you're going any faster than that, you're beating Usain Bolt, which you're probably not actually doing. You need to know the speed of sound in air. It's approximately 340 metres per second. They also allow 330 metres per second. It depends if you're at sea level, how dense the air is. There's a couple of things. And for all three of these, I've done a little, this means it's approximately symbol. The speed of light, however, in a vacuum does not have an approximate symbol because it's a constant. And that is 3 times 10 to the 8 metres per second, or 300 million metres per second, which is the fastest thing that exists. If you get a speed higher than that for anything, you're wrong. Okay, you need to know some methods to determine speed, and they're quite like this for a 6-mark question. So imagine you want to work out the speed of walking. This is an experiment I do with my students. For this, you'd need to measure a distance with a tape measure. Then you'd need to time how long it takes to walk that distance with a stopwatch, and you would then do speed equals distance over time. For any of these experiments, it's always good to repeat and average, and they always want you to say the and average bit there. And in terms of making this as accurate as possible, the bigger the distance you can make, the better, because the longer the time will be and there's less chance of human reaction time getting in the way. Speed of sound, there's a couple of ways of doing this, but one quite popular way is to have a clapperboard and have that clapperboard being held by somebody. And they are a large distance away from someone else, and that distance needs to be at least 300 metres if it's going to work. When we do it at school, we can't get that far because our field isn't that big, so we do it with about 100 metres and it doesn't work that well. You can measure this distance with a trundle wheel. You could measure it with a tape measure, but that would be quite laborious. A trundle wheel is one of those things that clicks as you pass it along. And then what happens is person 1 will clap the board, and person 2 will press start when they see the clapper clap together. Start when they see clapper, and they'll press stop on a timer. They've got a stopwatch. That's my terrible drawing of a stopwatch. When they hear the clapper, because sound travels much slower than speed. 340 compared to 300 million is much slower. So you'll see the clap happen before you hear it, and then we use speed equals distance over time. The distance will be your 300 metres. The time is the time between the clap and seeing it and hearing it. And you should get about 340 metres per second. That's the reason that when there's thunder and lightning, you can see the lightning and then you hear the thunder. The other way is using light gates, and this is more in the lab you'd do this. What you'd have would be a track. It could be either on a air track to try and get rid of friction, or you might have it on a slope with a cart, and that cart will have a piece of card attached to it, and then you'll have either 1 or 2 light gates. Now the light gates have got a little sensor inside them, and they sense when something goes through them. So when the card travels through the light gates, there's one of 2 things that can happen. We can either measure the distance between these 2 light gates, and then the light gates, which are connected to a computer or a sensor, will time the time it takes for the card to get between here and here, and then we do v equals x over t. Or you might have 1 light gate, my terrible drawing of a light gate, sorry, and the card going through, and you measure the distance of the card, and the light gate will then time how long it took for the card to get through, and it can work out the speed. Light gates are pretty expensive and therefore can usually do this for you. They work out the speed for you, or they can give you the time and you can then work out the speed. You use these also when you're looking at momentum and acceleration, which brings me on to acceleration. Now, acceleration is a vector, and it has a definition. It's the rate of change of velocity, and that is why it's a vector, and that becomes very important later on. It's the rate of change of velocity, and velocity is a vector. Now we know rate means divide by time, so I can write this acceleration as a equals the change in velocity divided by time. This is the Greek symbol delta. It means changing. In your GCSE, you're more likely to see this written like this: v minus u over t. Now v is the final velocity, and u is the initial velocity, which means then that v minus u is the change in velocity. T is hopefully, obviously, time. Now the unit of v and u is meters per second, and the unit of time is seconds, which makes the unit of acceleration meters per second divided by seconds, which is meters per second squared. It's an odd one, but there we are. This is the definitive equation, the one you'll probably use most often, but there is another equation, and you are given this in the exam. So you're also given on the back of your exam sheet, v squared minus u squared equals 2ax, which can be rearranged as a equals v squared minus u squared over 2x. So very often you're asked to use this in a core practical in year 10, in the forces topic, you might use this as well. Here, a, hopefully, obviously, is acceleration. And x, if we think back to the last page, x is displacement. So you're given this in the exam. Now that brings me on to one specific example, and that is falling objects. So falling objects. Now when an object falls, it's the force of gravity that pulls it down. Therefore, it's the force of gravity that gives acceleration. We have something called the acceleration due to gravity, and it has the symbol g. And for Edexcel, it has the it always has this, but the value of g is 10 meters per second squared. In reality, as you get higher up and you use physics further in the school, you might say that g equals 9.81 meters per second squared, but for Edexcel, the accepted value is 10, which is much nicer because it makes all the sums nice and easy compared to this one here. So I would always go for this because it's possible. Now, if I think about dropping two objects, I've got here a hammer and a feather. I know my personal experience, not that I've dropped a hammer and feather, but if I've seen it happen, the hammer will reach the ground first. That isn't because it's accelerating more quickly. That's because there's air resistance in the way. The feather has got a large surface area, it's quite light. The air resistance is quite large in it, whereas the hammer, it has much less air resistance, and therefore it falls more quickly. If there was no air resistance, then they would both fall at the same rate and they'd hit the floor at the same time, and their acceleration would be 10 meters per second squared. So after 1 second, they'd be traveling at 10 meters per second, after 2 seconds at 20 meters per second, after 3 seconds, 30 meters per second, and so on. We can see this actually happen on the moon. Many astronauts have had a go just to show people that it's possible, and you can see that it does actually work. But in Earth, you can't get rid of all the air, and therefore you would actually see that the hammer would hit first. But when we're doing mechanics at GCSE and A level, we pretty much always ignore air resistance. So you can do that there. So the final section of this little topic is motion graphs. You need to know about two types. You need to know about displacement time graphs, and you need to know about velocity time graphs. Now, both of these have got a scalar analogue. They've got distance time graphs and speed time graphs, which are quite similar, but you will never see lines going down or below the axis for distance time graphs. And for speed time graphs, you won't see this below the axis. So I'm doing the harder one, and then hopefully the scalar ones will be easier to cope with. So these two journeys look the same, but they are very, very different. Displacement time graphs tell us how displacement changes over time. Now this first section here, we can see that over time, displacement is gradually increasing at a steady rate. So this here is a steady speed. So for a displacement time graph, a steady speed is a diagonal line. like so, straight, diagonal. Then here we get a bit of a flat section. This is stationary, because this means that as time passes, the displacement isn't changing. So for stationary objects, a flat horizontal line is what we see for a displacement time graph. So stationary is a flat line, a straight diagonal line is steady speed, a curve is acceleration, because that means the speed is changing. It can be up or down. Slowing down is still a form of acceleration. It's often called deceleration, but it's still a form of acceleration. So acceleration is a curve, any type of curve that you want. And we've got another flat bit, so a stationary again. Then I've got a steeper line. Now a steeper line means a faster speed, but it's still straight, which means it's steady. So this is a higher steady speed. And the distance is now decreasing. Now this is the start point, the zero origin. So here it's going back to the start. So all of this is going away from the start and it's going back to the start. Then we've got another flat line. Once again, it's stationary. And at this point, it's stationary at the start point. And then here we're going behind the start point. So we've got a steady speed, but backwards. We've got a stationary point and then a steady speed going back to the start point, so forwards. And it's about the same speed, because we can see here the gradient's the same, which brings me on to this. The gradient of a displacement time graph is the velocity. Now, why is that? Well, gradient equals the change in y over the change in x. The change in y here is x, distance displacement. The change in y here is t. X over t, we know from before, is velocity. And the area underneath this graph means nothing, but it will mean something for the velocity time graph. So here's the velocity time graph. For the same looking journey, we'll have a very different actual journey. Here, this means that the velocity is increasing. So we've got here a steady acceleration. So for a velocity time graph, acceleration is a straight line like so. A flat line, that doesn't mean stationary. That means that the velocity is not changing, it's staying the same. So this point here is a steady velocity. And by the way, every time I said speed here, I should have said velocity. Apologies. So a steady speed or a steady velocity, I should write that here as well. Right, V, would be a flat line. Then curving means the velocity is changing again. So this is a different type of acceleration. This is a non-constant acceleration. So it's speeding up at an increasing rate, which is quite hard to get your head around. Then I've got another flat line. Once again, it's not that it's stationary, it's a higher steady velocity. So if I put some numbers on this graph, which might make it a bit easier. 1, 2, 3, 4. We can see that the speed's going up to about 2.5 maybe there, and then here the velocity is about 4 meters per second. Then we've got a straight line, but it's not horizontal, so this is acceleration. And specifically, it's deceleration, because the speed is going from 4 down to 0. This point here, this is where we are stationary, because here, the graph, the velocity is at 0. So this is stationary. And then these two here, these are both accelerations. This one is speeding up backwards. Think about the numbers here, they go negative like so. And then this one is slowing down, but going backwards. And then finally, this little section here, it's a straight line, which means it's steady speed or steady velocity, but backwards. Because a negative velocity means a velocity going backwards. So stationary here is a flat line on the origin, whereas a steady velocity is flat line not on the origin, although 0 meters per second is a steady speed. So the gradient here, if I use the same thinking, the gradient is equal to the change in y over the change in x. Now y is equal to v over x is t. Well, change in velocity over time I know is acceleration. And the area underneath, now the area underneath something equals the x-axis times the y-axis, that's v times t. And if I rearrange the equation for speed, speed times time actually gives me displacement. So the area under a velocity time graph gives me the displacement of that graph. So these are quite tricky. If I just kind of quickly walk the journey out with my fingers, what we've got here is I'm starting here, a steady speed going forwards, then it stops, then it accelerates and stops, then it has a steady high speed going back to the start. Then we're stationary for a little bit, then we've got a steady speed going backwards, stop for a moment, steady speed going forwards. However, for this journey, it's quite different, and it's quite hard, this one. We've got a steady acceleration, so we're speeding up to then a steady velocity, then we're going to speed up even more to a higher steady velocity, which I can't do because it's going off the page. Then we're going to slow down to 0. So let me try and do that. So speed up, steady velocity, speed up more, steady velocity, and then slow down to 0. We then stop, and then we have a steady speed backwards, and then slow down again. So this one's much, much harder to do. So that is pretty much most of motion. Caveat, I probably missed some bits out. Soz, didn't mean to, but it's quite hard to do the whole of motion in 21 minutes as we are. Hopefully it was helpful.